I'm happy to invite Tomer Ashur to speak about Algebraic Ciphers.
Yeah.
And Tomer is the CEO and founder of 3MI Labs. And yeah, thank you, Tomer.
Okay, yeah, thanks. Thanks for the introduction, David. So indeed, my name is Tomer. I have to apologize in advance. I haven't been on stage, I think, since before COVID, so I'm not sure I still have it. We'll see. Today's talk, it's not a talk, I'm not a professor anymore, but today's presentation is about advances in algebraic ciphers. I am Tomer from 3MI Labs. What's 3MI Labs? We are a research company in cryptography and Web3, providing commercialized research as a service, if you will. We are partners with the Wallet Labs, Polygon. We previously worked with Starkware and a few other companies. But that's not what you came here that's not what you want me to talk about. So I'm saying up front, this is the most cryptographically heavy slide that I have today. The background of algebraic ciphers is with Starkware. Starkware had their idea in 2018. They wanted to use zero knowledge for scaling Ethereum. And they realized quite early that in ZK Starks, you need a hash function for it. What is a hash function? It's a function that takes a string of arbitrary length and returns a digest of a fixed length. And for those of you who are less techy, we can informally say that it takes data and shrinks it to fixed size fingerprint. And just like the fingerprints of two people are supposedly not the same, this is actually not true in reality, but that's what we claim. The same holds for hash functions. They provide the fingerprint that is unique. And I'm sure that you've heard of some hash functions like SHA-256 and Chacha. Now, what we need, like I said, this is when Starkware came to talk to us in 2018. The motivation is for application in zero-knowledge MPC and FHE. And why is that? Such protocols have an algebraic structure by their nature. I think maybe I can tell you a secret from the cryptography world. There are two branches of cryptography. Like maybe more than two, but for the sake of this talk. So there's the public key people, and that includes theory, all the zero-knowledge MPC, FHE, and these are mathematicians. These are smart people who understand math. I'm not one of them. And mathematicians think in terms of algebras and prime fields and stuff. And you know, we say that the fundamental theorem of algebra, not we say, Gauss said it, that the fundamental theorem of algebra is that a polynomial of degree n has at most n roots. It sounds fancy. There's the other branch, the symmetric key cryptographers and the hardware acceleration people. We are engineers. We descend from engineers. The fundamental theorem of engineering is if it's ugly and it works, it ain't ugly. So we do stuff to make them work. That makes us somewhat incompatible, or at least has made us in the past incompatible. All these smart things, they come from the mathematicians. Okay, so what do we need to run a Stark-based hash function? At this point, we're only talking about verification of Starks, on how to make them efficient. We need a hash function that is efficient to verify in zero knowledge. And concretely, what we want is for this hash function to have a compact description like this. Yeah, okay, this isn't working. But like this, where you can write it as a polynomial or a set of polynomials, but something that mathematicians like. We need them to work in finite fields. finite field FQ. Now, these are two Matzy slides, and from there, it's only pictures. A field is a set F. So, for example, all the numbers between 0 and 11, not including 11. And we have two operations defined over it, addition and multiplication. Sometimes these operations don't look anything like the addition and multiplication you are used to. That's the name we use for them. Examples include the binary field F2 that has the 0, 1, XOR, and bitwise AND. F3, it's 0, 1, 2, modular addition and modular multiplication. And essentially, every prime number defines a field over the set from 0 to p minus 1 with modular addition and multiplication. And every power of a prime field also defines a field, we call it an extension field, from 0 to p to the e minus 1 with some addition and multiplication depending on what p is. That's it, I'm done with the math. So here's a counterexample of what wouldn't work well in a Stark. This is a stream cipher called Chacha, and you see that it mixes, we have here in green modular addition. That's the usual addition that we think of modulo a number, so like when we compute time. And the red parts are XORs. That's addition in F2. Now, again, as engineers and computer scientists, you give this to someone to implement, there's no problem. They'll write two lines of code, A plus B mod P, and then they'll use the result of that and XOR it with someone else, and you won't hear any complaints. For mathematicians, this slide is painful because it mixes operations from two different cinematic universes. Imagine Yoda working with Captain Picard to achieve a cryptographic goal. And incidentally, it's also the same people who don't like when we mix Star Trek and Star Wars that don't like that we mix modular addition and XOR. So this is not good for us. Luckily, there's the best cipher ever created, the AES. AES, in case you don't know, the Advanced Encryption Standard, is a block cipher co-developed by two Belgians and won the competition for selecting block ciphers that ran by NIST, the National Institute of Standards and Technology in the US. This was in the 90s. And it happens to be, this wasn't the plan, I can say that because one of the co-designers was my PhD promoter, so I can tell you that they didn't plan for this. It has an algebraic structure. AES works, the state of AES is this matrix that I have there. These are bytes, and being bytes, so we can call them bytes, but we can also call them elements in F2 to the 8. So already the state is algebraic, and then it has four operations. It has the S box. I'll go back to these two subpoints in a second. It has the shift rows, the mixed columns, and the add round key. The shift rows, mixed columns, and add round key are all linear operations, and unlike the real world or the other world, linear operations come for free, almost for free in ZK verification. So we don't mind having them. It's non-linear operations that don't come for free, and which is the case for the S-box. Now, on the other hand, security requires that you would have non-linear operations. You can't have security without including them. So now it's a trade-off between having the right amount of non-linear operations to ensure security, but on the other hand, not too much to not damage efficiency. So maybe I will, yeah, that's what I just said. So we said that the S-box is nonlinear, and in fact, it consists of two nonlinear operations. The AES S-box starts with the multiplicative inverse, that is y equals 1 over x, or the way we write it, x to the minus 1. And then a fine polynomial, which is here. I'm not going to read the entire polynomial. In a previous version of this slide deck, I had like the entire derivation of how and why the multiplicative inverse requires 14 multiplications, and the affine polynomial requires 7 multiplications. I decided to save you to save your time and not have it. So just trust me on this. But in AES, we can say that the total cost is 7 plus 14. That's these two operations. times 16, because we have a state of 16 bytes, times 10, and it results in 3,360 multiplications. And that is a good first order approximation of the cost of verifying AES in a Stark. But Starks have some cool tricks that we can use that are not available in the traditional computation models. And one of them is that for verification, we already know the answer. So we only need to verify it. Now, if y is equal 1 over x, it also means that x times y is equal 1. That thing requires only one multiplication to verify. And in fact, it requires two, because AES is not just 1 over x, but so we have two multiplications now. The affine polynomial has 7 multiplications, and this is actually inherent to the security. So we end up with having now AES, after we optimize on how we evaluate it, 1,440 multiplications, which is a good number, but we would like something better. This was still not efficient enough for Starks in 2018. So that's where we came along, and we invented a new hash function. Right? AES is a block cipher. Now I'm talking about hash functions. I guess that for most people in the audience, that difference doesn't matter, but it matters a bit if you want to be formal. So I'm just giving this disclaimer. The Jarvis hash function looked at what are the cost drivers of AES. So when we calculated the cost, there's a 16 there in the equation. That comes from the state of working with bytes. But there's no reason to work with bytes. You can work with one big element in F2 to the 128. And, well, OK, I'll actually talk about the cost in a second, but you can do that. We also took the affine polynomials, and we used the same trick that we had for the inversion, also with the polynomials. So we took two low-degree polynomials, both of them of degree 4. We used one of them directly, that's B, and the other we used its composite inverse. Now, the composite inverse of a linearized affine polynomial of low degree is a linearized affine polynomial of high degree, which is excellent. That's really what we want. And this property of Starks that you can compute in more than one way really allows to evaluate this efficiently. So the cost of Jarvis is 2 times 3 times 10, 60 multiplications. And there's only one problem with that. It's insecure. So, and unfortunately, it wasn't us who discovered this. It was someone else after we published it, as it happens. And this is the point where we understood. Again, I can't speak for all cryptographers, but I can say about myself. At this point, I was already doing symmetric cryptography for about 8 years. That's enough to develop a certain level of intuition about what works and what doesn't. That's what I thought. And then this showed me that all the intuition that I have as a symmetric cryptographer isn't necessarily true when we move to algebraic ciphers. And sure, I took it badly when this was broken back then, but it made me a better researcher because it forced me to start working from first principles. Can't take anything for granted, even if you have seen it work so many times. So Jarvis was insecure, but we can still do better than AES. So building on Jarvis, we did two things. You can't have just one field element. And to be honest, we don't yet know why. There's still so many open research questions here. We're not sure why. We know what would happen, but we don't know why there's a symmetry break when you move to 2 elements. Our new cipher is called Vision. It's now a vector of field elements, whatever size you want, whatever size support your Stark system supports. So a vector of elements, they go through the multiplicative inverse, followed by the inverse of the affine polynomial B, and then MDS matrix. Now you see in Jarvis, we only have the affine polynomials because the point of a linear layer, for example, an MDS matrix, is to mix elements. But if you only have one element, then there's nothing to mix. You don't mix an element with itself. Now we need, again, an an MDS matrix, which would affect efficiency later. That's why I'm pointing this out. And this is one step within the round. And then the other step, again, goes through the multiplicative inverse, followed by an affine polynomial and an MDS matrix. And to evaluate this, you can fold these two steps and represent them as a single round that is evaluated efficiently from the evaluator's perspective, but still remains hard to evaluate from the adversary's perspective. So that's vision. Okay, the cost, we've derived the cost for this. This cost is based on some mathematical reasoning. And I've heard that I'm not the only one who works with wishful thinking, squinting your eyes, and hoping, and experimental evidence. So this is less certain than what I would like it to be. I can't really justify this equation. I just know that it works in practice, and I have some arguments for it. A good thing is that nobody has broken this in 5 years, while many newer functions were broken, so I'm quite confident, at least that it won't happen to me again. In terms of the Stark systems that people use today, so I'll start with the second one, where we have m equal 12, so that's the number of elements in the state vector, and n is 64, that's the field size. Then you get 192 multiplications. That's already pretty good. I've seen newer companies working with, that are starting to work with smaller fields than 64. So when I started working with Polygon about 2 years ago, 64-bit fields were the state of the art. Now I can see companies starting to work with 32-bit fields. It would increase the cost of the hash function, but apparently it makes everything else more efficient, so I don't know. But it's still good numbers. But you know, the Bible says that there's no rest for the wicked. Every time we think we've got to where we need to be, then someone throws a curveball at us. We published this, and then people started moving to prime fields, because prime fields are more efficient anywhere outside my niche area of algebraic ciphers. And again, this comes from the fact that the mathematicians who are developing these things prefer, and there's something more mathsy about prime fields than binary fields. This brings us into an entire new domain of unknowns. Symmetric cryptography has not worked with prime fields. There are some maybe synthetic examples, niche cases, historical stuff, but mainstream symmetric cryptography has always been with binary fields. We have about 50 years of theory of symmetric crypto to build on about the properties of the building blocks we're using to design symmetric ciphers in the binary case, and we have none of that in the case of prime fields. We also don't know, and we have seen that it actually doesn't always happen, that some basic truths translate to the prime field case. There is a construction called Merkel-Damgård, that's a standard way of building a hash function, doesn't seem to be secure for prime fields. Not clear why yet. I see that Ben is also surprised by this observation, but it's true. Like, we see attacks. And the attacks that we are used to, so my background is in cryptanalysis. I actually come from breaking ciphers. There are two basic attacks in symmetric crypto. They're both statistical, differential, and linear cryptanalysis. And almost every paper you'd read opens with the sentence, differential cryptanalysis is one of the two most powerful attacks in symmetric crypto, the other one being linear cryptanalysis. Both of them don't apply the same way to prime fields. And so they are not important. I wrote a PhD thesis on something that is going to be obsolete. That sucks. And algebraic ciphers, the kind of that mathematicians do, which I am not, is actually very significant in this field. So we all have to learn our stuff. But surprisingly, attacks in public key crypto are often algebraic in nature, They don't translate very well also to this setting because of the completely different structures that we use. The public key crypto has a lot of randomness and entropy involved in each instance of the problem, where we have compact representations with a lot of redundancy, and it really changes the algebraic properties. So there's so much to study in this. And I'm, by the way, also having PhD students if anyone is interested. But of course, it's not that we decided, okay, we don't know how to build them, so we won't. We did what everybody in this room is doing and hoped. And we have Rescue, or we had Rescue. Rescue is algebraic hash function efficient for Starks over prime fields. It supports any prime field. We did notice that inversion doesn't work the same way when you move to prime fields. It took us a while to understand why, but we do now. If there's time, I'll give the answer. But instead, but we couldn't use inversion. So instead, we used something called a power map, x to the alpha. We need x to the alpha to be, or we need the exponentiation with alpha to be a permutation. There's a very easy way to check if a certain alpha is a permutation over a given field. You need a small prime. We first thought that that prime would be 3. In today's fields, 7 seems to be the smallest prime that is a permutation. And to have a high degree, like we still need a high polynomial degree, because again, cryptography, then we use the composite inverse, so x to the 1 over alpha. And because of folding that I've mentioned, that you can evaluate instead of 1 over x, you can do x times y equals 1. You can also do fold this round and evaluate it efficiently as if it was only power alpha without the high degree that is 1 over alpha. But I do want to stress this is for verification. We'll soon go to efficiency of proving. Yeah, the cost, I already gave my disclaimer. We get about 650 multiplications, quite independent of the state size. That's also something that needs explanation. But then we were asked, okay, so then Polygon came. Oh no, so this is still the Neptune project. They needed, so okay, at this point, verification was efficient enough. Now they want to start making proving efficient. After saying that it doesn't matter, they decided that it does matter. So we came up with a new hash function, rescue prime, where after this was, I think rescue was out already for 3 years by then, and we saw that attacks are not progressing, so we reduced the number of rounds from 10 to 8 and made a few more smaller changes. So rescue prime. All of these functions, by the way, are used in production in different systems. And none of them is broken. That's a good sign, or not broken yet publicly. And then we had the rescue prime, and that's where Polygon said, but we want to push it to the edge device to be able to create the proof. That requires that you improve the efficiency much more. So we worked on a hash function called RPO. The trick here is that the MDS matrix, this M block over there, is tailored to their field. So finally now all the other functions I talked about can work over any field, but RPO works over this field. It's called the Goldilocks field. 2 to the 64 minus 2 to the 32 plus 1. And we can then fix the MDS matrix, and that gave us something between ×2 and ×4 improvement in the proving time. And they still wanted a yet more efficient hash function. And that's now that at this point, the well is starting to dry. We've used all the tricks. We've optimized everything. What we need is to identify an operation that would be efficient, more efficient than the ones that we already have. And that's not easy. Like that's something you make a career out of. And so did I. So we introduced operations over extension fields of prime characteristic, of odd characteristic, that's the term. So this x to the 7 here is happening over a cubic extension field. So you take 3 elements in the base field, merge them together, and now they are 1 element in an extension field. And you run the x to the 7 on that. And that does good mixing and is more efficient than the other tricks. And that allows to remove some of these rounds, the 1/7, which are the performance bottleneck, but are necessary for security. Now I'm venturing, so this was past, present, and now I'm venturing into the future. We are looking into having a version of Xash that is Xash 8, where we don't, in this layer, we don't have all the 1/7s, only some of them. That seems to be still fine. We're pretty confident that this will still be secure. And the effect is direct, like you remove 1/7, it saves time, that's immediate. We're also considering, in terms of future direction, to have an Xash 4, so only 1 out of every triplet would have the 1/7 operation. That one already starts to be shaky in terms of security. We think it's secure, but we're really finding it hard to argue this security formally. So to complete this, we would need a more evolved theory for the security of algebraic hash functions, the thing that I said that we don't have. Another direction that I'm seeing, we're working with Ulvetana, that's a hardware acceleration company from Serbia, to, well, they do hardware acceleration. They created their own zero-knowledge proof system that is Stark-like. It's called Binius. It works again over binary fields. So we went back to Vision, and this is our design for them. So that's Vision again, but they have had, now we're again improver efficiency. They had problems with the high degree of this, and sometimes all it takes is a small observation. So the usual way to represent this B to the B inverse would be in polynomial form, and that would eat up some resources. But noting that this is an affine polynomial, you can also represent it as a matrix multiplication with bits. And then it's super efficient in hardware, and it's exactly the same thing, doesn't require to change anything. And that's possible because of their new system and because they work in hardware. So in software, it probably would be less efficient. What else? We also see, okay, so I was unfortunate to miss most of Zvika's talk this morning. I know that he spoke of FHE. I don't know if he mentioned transciphering. One way to improve the communication complexity of in FHE setting is that you symmetrically encrypt the text on the user side, then upload it to the FHE server, and then decrypt homomorphically that string. We developed a cipher called Chagre that is super efficient for this decryption. It is about 2 or 3 times faster than AES in this context. And AES is already pretty good for FHE. Yeah, okay, that's how it looks like, but I don't have time. Yeah, okay, there's also represented R1CS, I'll skip that. But the last thing I want to mention is beyond hashing. So now we have hash functions for the star case, but if you want to do privacy, if you want to add privacy using zero knowledge, you're going to need to encrypt stuff. And this is something also D-Wallet are interested in, on how to encrypt in a way that would be efficient to verify in zero knowledge. So we are also designing authenticated encryption schemes and the protocols to use them. And I believe that's all right on time. Thank you all for listening.